because just the lineup is just mind-boggling, and yeah, I'm probably the 106th person to say that, wow, there's a lot of speakers, but wow, there's a lot of speakers. Lots of great talks, so thanks everybody who's given talks. It's super interesting. Yeah, so this is joint work with my PhD student, Grant Fickus, who's at USC. And I advance the slide. There we go. So yeah, we actually came at this from a weird angle. We started by looking at, well, some spectral graph theory, which is I spent a lot of my time doing, namely the algebraic multiplicity of 0 as an adjacency eigenvalue of hypergraphs. I got a lot of things in parentheses there because, well, you can study geometric multiplicities, and you can study the Laplacian eigenvalues and other kinds of matrices associated with graphs. Also with hypergraphs, which actually spend maybe more time on than spectral graph theory. But this is mostly I'm going to talk about the graph setting, because the hypergraph setting is just a mess. It would take me an hour even to define it. Yeah, the adjacency matrix, actually, this Alex before the break defined it. What do you call it? Edge function or something. So this is just the you put a 1 if there's an adjacency between two vertices and a 0 otherwise. This is the simplest matrix associated with a graph. And okay. So the characteristic polynomial is just the characteristic polynomial of that matrix. Of course, this is the adjacency characteristic polynomial, but if somebody says it's characteristic polynomial, they probably mean this one. And its roots, of course, are it's a multi-set, the spectrum. So it's called the adjacency spectrum, or it's the most common spectrum that people study. And again, here we're going to be concerned mostly with algebraic multiplicities, but in general, there's also geometric and other senses in which one might study multiplicities. So the big question that we were starting from was, what's the multiplicity of 0? Surprisingly little is known about this. You'd think it's a natural question. If you're familiar with this result, the multiplicity of 0 for the Laplacian is the combinatorial Laplacian is just the number of components. So you might think some nice simple answer like that would be true for adjacency matrices, but seems not to be the case. Trees are pretty well understood from this perspective. Also, there's lots of graph classes where people have computed the multiplicity. It's not hard, for example, for cycles or complete graphs. Simple exercise. But in general, very little is known. So we don't know, just glance at a graph, what properties predict the multiplicity of 0. Let me just refer to the characteristic polynomial of some graph G, fixed G. I'm going to refer to it as F to make life easy. So the multiplicity of 0, of course, is the largest non-negative integer m, so that if you divide f of x by x to the m, you just get a polynomial. Right, the number of times is divisible by x. Let me write bar over a polynomial for its reciprocal. The reciprocal of a polynomial is the polynomial you get by reversing its coefficients. It's also the polynomial whose roots are the reciprocals of the roots of g. Of course, if 0 is a root, you got a problem. But we're getting rid of the zeros here, right? This is g is f divided by x to the m. So just to point out, if you take the log of this reciprocal polynomial, and it's just a little technical hiccup that you have to subtract off the log of g of 0, which is the constant term, but that was the leading coefficient back when we were talking about f. That's a sum over, if you think about it for a second, because we're taking the reciprocals of the roots, it's the sum of the log of 1 minus bij, where the bi's are just enumerating the roots of g. And that in turn, of course, you can write that, assuming this converges, but let's just treat it formally for now, that you could write it just using the Taylor series for log, and it looks like this, right? So just to point out the coefficients here, you have these bi's, and they're being put to the jth power and divided by j. And it's a sum over all the i's. So let me rephrase the question. We're looking for the smallest r so that if you multiply those coefficients by j, you get something that's a sum of r different jth powers. That's what was written on the previous slide. I can't go backwards. And those CJs are the coefficients of the log of the reciprocal of G. Why perform these crazy complicated transformations on G just to get at the multiplicity of 0? Well, it's because often we actually do have lots of information about the coefficients of log of the reciprocal of G because, well, if you write it using the definition I just gave you for what G is and then replacing it with F, it's the reciprocal polynomial, pull out the powers of X, well, and then replace F with the characteristic polynomial. The degree of G plus M, that just restores the degree of the polynomial, that's N. And then you can write the log of the characteristic polynomial this way, because we plugged in 1 over X. And then let's push the X to the N back inside. That gives you log determinant of I minus A times X. And by this amazing fact that log determinant equals trace log that I learned way too late in life, that is equal to the trace of the log of I minus A of G times X, where, we're think of log as, again, formally just using the power series. That in turn, there it is, there's the power series, is the negative of the trace of this infinite sum. That's just the power series for log. And then trace is linear, so you can pull it inside the summation, give you trace of the adjacency matrix of the J. The trace of the adjacency matrix of the J, that is just the number of closed walks of length J in your graph. So this has a nice simple form. And actually this is one way of viewing the Harari-Sachs theorem, if you're familiar with that. It gives the coefficients of the characteristic polynomial of the graph. All right, what we wanted to do in studying this is, let's find some different angles to describe this decomposition into powers, the number of terms we need in the decomposition of powers, because that's the thing that'll tell us what the degree, the order of 0 is. And I'm going to list a whole bunch of properties in a minute. Some of them are well known, but they're buried in the literature in different in an amazing range of topics. Signal processing, invariant theory, generating function theory, moment problems from measure theory and probability theory, Hankel matrices and Hankel transforms, total positivity. These are all, it turns out they're all connected with this topic in a really integral way. So some of the things I'm going to list, some of the properties are genuinely new. Some of them are not. It's a little hard to even attribute some of them because they're all over the place in these areas. Also not an expert in most of those areas. The TFAE I'm going to state, or there's actually 2 of them, that's also new. So of course we say that a complex sequence, it doesn't have to be complex, but just stick to that. It satisfies an rth order linear recurrence if there's r+1 coefficients, so that this equation holds for every, well, I should have shifted the index of C. That should be C sub I plus T for all T. Well, the characteristic polynomial associated with the recurrence is just you replace the linear recurrence with the polynomial. So take the coefficients directly to the coefficients of the polynomial. And we'll call a linear recurrence simple if its characteristic polynomial has all distinct roots. When it is simple, that means that there's a set of distinct non-zero complex alpha i's, so the beta i's are distinct, the alphas not necessarily, so that the CN can be written as a linear combination of the powers of betas, which should look familiar from what I was just saying about writing the coefficients as a sum of powers of roots. So let's define the moment rank of a complex sequence. So I'll just write M rank of the sequence to be the smallest R, so that there exists some non-zero alphas and some non-zero distinct non-zero betas, R of them, so that CN is this sum. And we're looking for conditions equivalent to the moment rank being equal to R. So previously, I pointed out that, well, okay, so R is the smallest positive integer, so that C sub n satisfies an rth order simple linear recurrence. And this has a few different names actually. That when you talk about R being finite, that's really got a number of names in the literature. It's called, well, sometimes you have to write out a whole sentence and say the existence of the finite linear recurrence satisfied by a sequence. It's also known as C finiteness. Sequence, also known as P recursive, has this property that, depending on what area you're in, it has a few different names. This notion of moment rank, it's well defined. That's not hard to see, but I'll point it out in a minute. One way to see it immediately. So here's an equivalent condition to having moment rank R. We'll use some polynomial algebra to get it. Let's write this script R sub C to be the set of characteristic polynomials associated with all of the different linear recurrences, not necessarily simple, satisfied by a sequence. So not hard to see. This is an ideal in the univariate polynomial ring. And since that ring is a PID, there's a polynomial that generates that ideal. You might guess that that is our polynomial that witnesses this this rank, and indeed it is. Its degree is exactly the moment rank. To see that, notice that the moment rank is R if and only if R is the smallest positive integer, so that the sequence satisfies a simple linear recurrence of order R. It's meaningful if F has distinct roots. We bake that into the definition of moment rank. And well, it's going to have distinct roots if and only if the ideal it generates is radical. So the moment rank is R if and only if its recurrence ideal is radical and its generator has degree R. There's another equivalent property, Hankel matrices. So given your sequence, let's write H sub MT to denote the m plus 1 by m plus 1 Hankel matrices matrix obtained from shifts of the sequence. So just to give you precisely what I mean by that, the ij entry of this H sub MT matrix is just C sub T plus ij. Just by way of example, if Cn is just n when n is greater than or equal to 0, then for example H10 is this 0, 1, 1, 2 matrix. As we start with 0 and it's 2 by 2 because that first parameter m is 1, and then H25 starts with 5 and it goes up 2 more terms, 5, 6, 7, etc. That's what these Hankel matrices look like. Any matrix with this structure is called a Hankel matrix. You could just give its the first row and the last column as its generating sequence. So suppose you had a sequence of moment rank R. Let A be the column vector of coefficients of that rth order linear recurrence that it satisfies. Since multiplying by that vector, multiplying your Hankel matrix by that vector gives you 0, that's exactly implementing the dot product that occurs in the definition of the linear recurrence. Then, well, the matrix has to be singular, right? Because we've just found a non-zero vector, which when multiplied gives you the 0 vector. So, okay, so that matrix is going to be singular when there is such a matrix A, or a vector A. And yeah, so, okay, the null space, it turns out it has dimension exactly 1. And in fact, the null space as you increase T, that's the size of the matrix, recall, doesn't change, so that you get the same null space as the size of the matrix grows. Of course, but equal, I have to be a little careful because there's the dimensions changing, but you can guess what this is. And the determinant is actually non-zero when you drop below the size that I meant, and where the determinant becomes 0 as noted above. So all three of those properties listed above, together with the assertion that A is in the complement of the affine R discriminant variety, this is just saying the characteristic polynomial has no repeated roots. That's another way to say that the moment rank is R. Also, if you have a sequence, moment rank R, let H infinity be, you can keep going with that Hankel matrix and just use the full infinite sequence, or one way infinite sequence, right? If you populate an infinite matrix with those entries, then okay, you can write the CNs as the powers that we're aiming for with the definition of moment rank. And let's define V sub R infinity, or I'll just call it V, be the infinite van der Waals matrix generated by the BI. So this has got the powers of beta I in in each of the rows, in the ith row. Then not hard to see that this relation between the C's and the alphas and the betas, that's just saying that H infinity is V transpose D V, where D is the diagonal matrix where the entries are alpha I, beta I. Turns out, okay, not hard to see, V and D both have full rank, they're rank R. And also that implies that this H infinity has rank R. So in fact, another equivalent property is that H infinity having rank R and emitting a van der Waals decomposition in this form is equivalent to having moment rank R. All right, so suppose you have a sequence that satisfies a simple rth order linear recurrence with R minimal. Then you do the usual thing, right? So you multiply the generating function by polynomial, the characteristic polynomial. Of course, the infinite part of this convolution goes away because it was the linear recurrence that the sequence satisfies. And you end up with just a polynomial. And so divide both sides by the polynomial on the left, and you get an expression for phi that's just some rational function. And so moment rank R is having moment rank R is equivalent to the sequence having a rational generating function with R simple poles. And that's one way to see it's well defined, for example. So here's the sort of big TFAE. See, the following are equivalent. C has moment rank R. It's the smallest integer so that C satisfies a simple rth linear recurrence, so rth order linear recurrence. Those finite Hankel matrices have non-zero determinant when they're R by R. And the null space is dimension 1, and then the kernel is the same as you look at translates. And then also the kernel shouldn't be contained in the affine R discriminant variety. That's the simplicity. The ordinary generating function is a rational function with R simple poles. That infinite Hankel matrix has rank R and emits a non-degenerate van der Waals decomposition. The recurrence ideal is radical. It contains the roots of any perfect power. And it's generated by some degree R polynomial. And finally, this is, you might wonder, why was I calling it a moment sequence? Well, it's because this is the same thing as being the moment sequence of a complex R atomic measure on the complex numbers. So if you have a measure on the complex numbers where it's complex valued measure, not the ordinary Borel measure, and it's R atomic, that is, it's made of just R atoms. So the entire measure is supported on R points. Then C being the sequence of moments of that distribution is equivalent to the rest of these properties. Also equivalent, this goes back to Sylvester. If you define this strange form that involves some binomial coefficients, then the form has, notice its degree 2R, it has wearing rank R. Wearing rank is this thing. A binary form of degree D has wearing rank R if you've got a bunch of complex numbers, so that basically F can be written as a sum of R dth powers of linear forms. So that's wearing rank, and turns out that's also equivalent to these other properties, having wearing rank R, and there's some little condition like the lambdas have to be distinct or something. Also grow exponentially, but it's not difficult to see that you need these things. Actually, what I just said is not directly applicable to the original question of computing the multiplicity of 0 as an eigenvalue of a graph, because the other multiplicities might be greater than 1. We need a slightly different definition that is going to use a lot of the same ideas. Define the unitary rank of a sequence to be Well, we got rid of the alphas, and now we're allowing the betas to repeat. So think of the alphas as being 1. Also, the index is shifted from 0 indexed to 1 indexed. So we're just writing Cn as a sum of powers of R betas instead of linear combination of R betas. And notice they can differ. This is really a different definition. The moment rank of the sequence, for example, 2 times 3 to the n, the moment rank is 1 because it's just a sum of 1 power with the coefficient of 2, but the unitary rank is 2 because you need 3 to the n plus 3 to the n to write it as a sum of just 2 powers. Basically, all of those statements, or most of the statements, are which were equivalent to moment rank, they also translate over to equivalent properties to unitary rank. But I just want to mention there's 2 others that are worth mentioning, 2 other properties. One is you have a sequence of unitary rank R, consider this strange function. So take the ordinary generating function of the sequence, and let's multiply it by x, take the negative and integrate it. Why do that? Well, because you get the sequence we're looking for, the Cn over n sequence. And when you exponentiate that, notice what happens. Of course, we wrote the Cn's as the sum of these beta I to the n's. And so just rearranging a little bit, turning the sum into a product. And then, well, that's just log inside the parentheses. And of course, those cancel. Oh, you just get a polynomial. So that funny exponential is a polynomial. Being the log of a polynomial is also equivalent to having unitary rank R. So, right, so the unitary rank is R, it's equivalent to that exponential being a polynomial of degree R with non-zero roots. Also equivalent, C is a moment sequence of a complex finite atomic measure on the complex numbers, where the masses are, actually, they're not just complex, they're just positive naturals, but they have to sum to R. So it's a different kind of moment problem. And just one final note, we're sort of hoping to use this for things other than just the degree of 0 as, or multiplicity of 0 as an eigenvalue of graphs. A lot of work has gone into analyzing the recurrence rank, the smallest R, so that a sequence satisfies a order R recurrence. Just for example, here's a famous open problem that you don't know about it. Just want to mention it. The avoidance sequence, AVN of 1, 3, 2, 4, that's the number of permutations of length n that avoid the pattern 1, 3, 2, 4. In other words, there's no I1, I2, I3, I4 in sequence so that they have the same order as 1, 3, 2, 4. It's order isomorphic to 1, 3, 2, 4. The generating function of this sequence begins thusly, and it's known up to degree 50. A little bit surprising because you think it's not hard to, it's not easy to compute these terms as the degree grows. But it's unknown if the moment rank is finite. So it's unknown if this satisfies a finite degree linear recurrence. It's an amazing problem. A lot of work has gone into it, and the techniques are getting more sophisticated. Actually, we're sort of hoping to use these methods on that question. Haven't gotten that far, but you can use this to show that the finite rank is equivalent to the existence of a finite atomic Borel measure, ordinary measure on the reals whose moment sequence is a complex numbers. This is the finite support case of the classical hamburger moment problem. And actually the Hankel matrices that arise in this case are believed to be totally non-negative, or actually totally positive, essentially the semi-definiteness. And that turns this problem, the hamburger moment problem, into the Stieltjes moment problem. This is Borel measures on the positive part of the real line, non-negative part of the real line. This is exactly the perspective taken by a bunch of recent work on these avoidance sequences, in particular this very nice paper of Boston, Price, Gutman, and Mayal that came out recently. So with that, I'll thank you.
Thank you very much, Joshua. Any questions for our speaker? If not, then I thank Josh again for a very nice talk. And the next talk is in 5 minutes.